welcome again to another fun-filled day of differential equations. Today I'm going to introduce you to a new method of solving differential equations. We're going to, step away from series solutions. It's good to know that we have those series solutions always in the back of the tool bag there, so that we can always grab it if we need to. But obviously, they're kind of a pain. There's a lot of work involved. So if we can avoid it, we want to, right? So I'm going to show you another method, or introduce you to another method today. We'll talk about it over the next couple of days. But it's this thing called the Laplace transform, which is another way to help us solve differential equations. But before I get rolling and doing my thing, do you guys have any questions on any of the homework or anything you'd like to talk about from previous classes? All right, well, I'm not seeing anything and I'm not hearing anything. So yeah, we'll go ahead and dive in. All right. So let me actually just jump right into the Laplace transform, and we'll talk about what it is and what it does and how it behaves. All right. So this is called the Laplace transform, named after the French mathematician who came up with the idea. You'll see Laplace's name all over the place. He was one of the biggies. I want to say he was in the 18th century, but I'm not 100% sure on that. But anyway, Laplace transform. What this is it's a linear transform. And I know that you guys talked about that in linear algebra. So this is the kind of thing that when you do a Laplace transform, if you got like a sum, the sums carry through, constant or scalar multiples carry through, all that kind of stuff. But it's a linear transform that uses an integral. So you'll also hear it sometimes called an integral transform. And there are lots of integral transforms, but the Laplace transform is just, it's a very specific one. All right, so the way that the Laplace transform is defined, and the notation you're going to see for this is you'll see the curvy L standing for Laplace. Then you're going to get one of these little like curly braces kind of things. And then in here is going to be your function. So we're always going to be doing the Laplace transform of a function. And it's defined as an integral from 0 to infinity of e to the negative st times f of t. All right, so I'm going to go ahead and put a little box around that, because when we do the Laplace transform, it's always the same. We always take our function, we multiply it by e to the minus st, and then we integrate from 0 to infinity. Now, there are two variables here, so I just kind of want to remind you that t, this is the integration variable. And so s, this is just treated as a constant. So think about what's going to happen when we integrate this thing with respect to t. We're going to get whatever, and then we plug in 0 and infinity. The Laplace transform ends up being a function of s. So there's still going to be s's in there. And so I'm just going to go ahead and put here equals, I'll call it big F of s. So the Laplace transform is taking us from the t world to the s world, but it's being done in this very specific way. All right, so let's just talk about this a little bit before we actually calculate some of them and think about some of the things that we have to worry about. So first of all, this infinity can potentially lead to some issues, right? Hopefully you remember when you have these improper integrals that sometimes they converge and sometimes they diverge. Excuse me. So specifically, the Laplace transform, this is only going to be defined when the integral converges. So what that means, some consequences of that, one is not all S will work. So given a function, excuse me, and you find a Laplace transform, there's often a restriction on the S. Like we'll say, okay, for this function, its Laplace transform is blah, but S must be greater than 0, or S must be bigger than A, or whatever. So get used to that. We're going to see restrictions on S. The other thing that's going to happen when we say it's only defined when the integral converges is that not all functions will have a Laplace transform. So there are functions that you just can't do the Laplace transform on. Okay, that just is the nature of this thing. But you have seen that. I mean, you actually have, maybe not with functions, with transformations, but think back to linear algebra when you did transformations. They didn't always apply to everything, right? And so, maybe it worked on a subspace of a given space. All right, well, it's the same kind of thing here, right? We're not going to be able to do this to everything, but we're going to be able to do it to anything where this integral actually converges, where we get a finite value. All right, so just some consequences of the infinite thing. Now, I do want to point out and show you that this is a linear transformation. And it's a linear transformation. It's pretty easy to see, actually, right? Like, think about what you need for a linear transformation. Is that addition carries through, as does scalar multiplication. So hopefully I'm not telling you anything you haven't heard. I'm sure Larry talked about this last quarter, but this is what it means for there to be a linear transformation. Well, it's pretty easy to see why that must be, or why that works for this, right? If we just prove that real quick, we're doing the integral from 0 to infinity of f plus c times g times e to the minus st. And then by the rules of integrals, we can split this into f times e to the minus st plus c times integral from 0 to infinity of g e to the minus st, which, yeah, there you go. That's those. So because of how it's designed, it is a linear transformation. And we like that, right? Linear transformations make everything easier. But yeah, there you go. All right, so yay, we define this thing as a linear transformation. It's the Laplace transform. Okay, well, let's do a couple. Let's do a couple of functions just so you can kind of see this process. You can get a feel for how it's done. And, then we'll start talking about why we use it, or what good it's for, or what good it does. All right, So let me go ahead and clear this real quick. And we'll actually do one. Actually, I'll leave the definition of it up. But let's do it on the side here so we can just always come back to the definition. All right, so let's do this guy. Let's start really easy. Let's do the Laplace transform of 1. So it's a constant function. It's just 1. So that means we're going to integrate from 0 to infinity e to the minus st times 1. So that's the integral of e to the minus st. All right, well, e to the minus st, that's easy enough to integrate, right? We're going to get e to the minus st divided by minus s, so minus 1 over s times e to the minus st, evaluated at 0 and infinity. Now, I'm going to be lazy here. I'm not going to write limits and all that. We're just going to plug in infinity. So we get minus 1 over s, e to the minus s times infinity, plus, because we're subtracting a negative, 1 over s. Okay, now, this is where we have to come down to the, I subsequently have erased some of it, right? Where it's like, there are going to be restrictions on our s. This is where this is going to come about, because we want to look at when is this actually going to give us a finite number.
S would have to be equal to or less than 0, right?
Say that again,
I mean, equal to or greater than, sorry. It can't be less than 0.
Okay, so it's all going to be about on which side of 0 we happen to be, right? If s is positive, so if s is greater than 0, then e to the minus s times infinity is now going to be a negative, really big number, and that's going to go to 0. If s is negative, then negative s times infinity is positive, and this blows up to infinity. So
and it can't be equal to 0 because
yeah,
I don't know. I messed up twice.
It's all good. But yeah, s equaling 0 is a bit of an issue then, because we're trying to divide by 0 and that doesn't work. In fact, if s equals 0, let me just show you this real quick. We'll get this out of the way. Let's go to Laplace transform when s is equal to 0. Then we're doing integral from 0 to infinity of f of t dt. Excuse me. And you can see that it's going to be really dependent on what f of t is. It's going to have to be something that has a convergent integral. So it's going to have to be going to 0 as we go to infinity. It's going to have to be going to 0 fast enough, right? And so when s is 0, it just turns back into a regular old improper integral. All right, anyway, so for this one, immediately we're going to say, well, we got to have s greater than 0. And if s is greater than 0, then this piece is going to go to 0. And what we're left with is just 1 over s. So the Laplace transform of 1 is 1 over s. But again, we know that s has to be greater than 0. All right, so that's how Laplace transform is done. Give me 1 second here, guys. I totally got something in my throat. I'm going to grab some water real fast. Give me 1 second. All right, sorry about that. I blame the fact that I don't have a nice high quality root beer here with me right now. Anyway, all right. So there's the Laplace transform of one. So let's try another one. Let's make something that's a little bit more complicated. Oh, but by the way, you now know how to get the the Laplace transform of any constant. Because remember that this is a linear transformation. So if we wanted to say take the Laplace transform of 17, it's going to be 17 times the Laplace transform of 1, which is 17 over s. You want the Laplace transform of negative 32? No, it's negative 32 over s, and so on. So we're going to make use of the fact that it's a linear transform to help us when we get to more complicated, bigger kind of functions. All right, so there is the Laplace transform for 1. All right, how about we do this guy? Let's come down here, change color so we know we're doing something different. And how about we try the Laplace transform of t squared? All right, so this one we're going to integrate from 0 to infinity of e to the minus st times t squared. All right, now if you integrate this thing, how are you going to do, if you had to do it by hand, what method would you use?
Guessing partial fraction.
It's not partial fractions, but I think you just misspoke, Victor. The partial fractions are the one where you have fractions that you split apart. This one you do integration by parts.
Yeah, that.
Yeah, I figured it was just a misspeak there. But yeah, so you'd integrate this by parts. So what I'm going to do, because I'm lazy, I'm going to go ahead and just use my calculator to get me the integral of this. I'm not going to plug in the bounds just yet. All right, so what you get before you plug in the bounds is 1 over s cubed time, or negative 1 over s cubed times e to the minus st times s squared t squared plus 2ts plus 2. All right, so now let's look at what happens when we plug in the 0 and the infinity. If we look at this piece, the s squared t squared plus blah, 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 that's going to blow up to infinity, because infinity squared, yeah, it gets really big. It doesn't matter what s is. That's going to blow up to infinity. So that's only going to be countered by this thing going to 0. So that one going to 0, we have the same conditions as before. We know that this is only going to converge when s is greater than 0. And when it does, the e to the minus st overrides the rest and drops that bit to 0. So in that integral, we're going to get 0 minus, well, negative 1 over s cubed. This is going to be e to the 0, which is 1. Here, we're going to get 0 plus 0 plus 2. So this ends up being 2 over s cubed. So there's your Laplace transform for t squared. Which of course now means we also know the Laplace transform of 4t squared. We actually know the Laplace transform of t squared plus 1, because we can actually combine what we found here when we've got things that are made up of both. So for example, let me just quick erase this. We'll leave our answer to the Laplace transform of 1. So if we were to say take the Laplace transform of 3t squared minus 2, this is going to be 3 times 2 over s cubed minus 2 times 1 over s, which is 6 over s cubed minus 2 over s. So check it out. We're actually able now to do Laplace transforms without doing the actual integrals, because we know the Laplace transform of the building blocks. So this is one nice thing about Laplace transforms, is once you kind of have fundamental functions down, you can get tons of stuff by just combining those Laplace transforms of the fundamental pieces.
So then, as long as you have the Laplace transformation for like enough building blocks, you can essentially never have to really do the integral again. You can just...
Yep. Yeah, exactly. You do it one time, you do the integral once, and you're done. And in fact, if we really wanted to be good about this, instead of doing t squared, we do t to the n. Do it generically with just t to the n. And then we'd know a formula for t squared, t cubed, t to the 5th, t to the millionth, and so on. So yeah, so what we're going to want to do really is start generalizing even more. So let me give you an example. We'll do another one here. Let's do the Laplace transform of e to the at. So this is going to give us every exponential function. Every exponential function could be written in some form of this, right? You just vary your a. So this way, we're just going to knock them all out at once. So we go to definition. Okay, great. So that's 0 to infinity, e to the minus st times e to the at. If I combine, I get e to the a minus s times t. So integrating that, I'm going to get 1 over a minus s times, whoops, integral is gone because I just integrated, times e to the a minus s times t from 0 to infinity. So that gives us 1 over a minus s times e to the a minus s times infinity minus e to the 0. All right, well, e to the 0 we know is just 1. But let's think about what's going to have to happen to make this converge. What's the condition we're going to need on s? Like, what do you know has to be? Oh, go ahead, Jesus.
No, I was gonna say a equals s, but that doesn't work.
Okay, so if a equals s, then we've got kind of that same problem before where we're dividing by 0. But we need a minus s to be negative. Because then we get a negative infinity as that exponent and it drops to 0. So this is only going to work if S is bigger than A. So there's a restriction on the S, just like I said before, right? We saw before, but this one, notice that it depends on what function we're putting in. So if we did e to the 2t versus e to the minus t, we're going to get a different restriction on the S. But for sure, S has to be greater than A. When S is bigger than A, then this becomes 1 over A minus S times 0 minus 1, which gives us 1 over S minus A. The minus sign just switched the order of those things. All right, well, there you go, guys. You now have the Laplace transform for any exponential function. Done. So with that,
Can you combine those two? Like 3t squared plus e to the at?
absolutely. So like, let's do that. Let's do a Laplace transform of 3t squared plus a e to the 4t. We'll even specify our a. Okay, so the 3t squared, that's going to give us a 6 over s cubed, right? Because it was 3 times 2s cubed. And then this one plus e to the 4t. Okay, well, that's going to be plus 1 over s minus 4. So hopefully you're seeing the power of this guy right here. E to the at, since we just did it with plain old a, we are now golden, 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 golden. It doesn't matter what exponential function, we're good to go. All right. So this
What
is
about
the
an exponential function where it's e to the power of? Wait, never mind. Never mind. Sorry, I just kind of for myself.
You answered it yourself. Okay, so like let's say, well, what if we had an exponential function that was like e to the t squared? Obviously, that's a different form than this guy. So we would have to do e to the t squared. So we could do, we're not gonna, but we could try say, well, what if we wanted e to the a t squared? Okay, well, if we run through that and we get a formula for it, okay, cool. That's good. Going to cover us for all of those things, right? And so, and you can do the same thing. Like we could do the Laplace transform of sine of t. It probably would be better if we did the Laplace transform of sine of at, because then we cover all possible signs. But then you might go, well, what if I want sine of e to the t? Okay, we'll do sine of e to the t. Right, so you can literally do any that you want, or attempt to do any that you want. And the reason I say that, because remember, sometimes you're going to get forms that are not, that just will not converge. There are certain functions that when you put them in a Laplace transform, always give you a divergent integral, just, and you never can get away from that. But barring that, do whatever you want. So this has already been done. This is already.
Is that what the Laplace table in our class file is?
That is exactly what that is. I'm going to pull that up here just to show you. Because if you go into the Canvas shell, right, in our class, there's the thing of files, right, where the syllabus and some other things lie. And there's one that's called Laplace table. This has already been done, right? This has been done. Everything, any function that you could think of trying to find a Laplace transform for has already been thought of and has already been done. So we're gonna like not reinvent the wheel, and we're just gonna go ahead and use this. So here is a table that has all kinds of Laplace transforms. All right, so I know that there's a lot of other stuff that's kind of written up here, but here's how to read it. So this is f of t. So this is the function that we're putting in a Laplace transform. And then this is the Laplace transform, big F of s. So think about the ones that we've calculated so far. We did 1, and we saw 1 over s. We then did t squared. And notice that t to the n always gives you the same form. So t squared was 2 factorial, also known as 2, over s cubed, right? We saw that. And then we did e to the at. We just did that right now. I got 1 over s minus a. But just wanted you to see that, no, that these are known for all kinds of different things. So here you see the square root, here's sine, cosine, here's t cosine, here's cosine plus t sine, here's sine of whatever else on the inside. And you notice that the forms, I mean, they definitely get more complicated as we go down, but all right, they are what they are. I mean, here's hyperbolic, right? There's sinh, gives us this guy, right? Now, this table does also have a lot of things that you don't know about, that we've never talked about, that just, yeah, aren't relevant to us yet. Some of them we will learn about. But so that's why when you see something like the Heaviside function or the Dirac delta function, that's that guy. So here's the Heaviside, here's Dirac delta. We'll get there, right? But also notice, check this out. There's a formula for the derivative. There's a formula for the second derivative. There's a formula for higher order derivatives. Those we'll talk about. Those we'll actually calculate. But anyway, so, and there are just a couple of notes here about them, just to remind you of some of the things that can come about. Another one that's kind of interesting is this thing is called the gamma function. Just so you know, the gamma function, if n is an integer, is a factorial. And if it's not an integer, gamma function works like that. So like if you had gamma of 4.1, it's 4.1 times 3.1 times 2.1 times 1.1 times the gamma function of 0.1. Anyway, just there are all kinds of little quirky things, but just realize that this table is more than enough for anything we're going to do, but we can use this to help us actually find Laplace transforms of other things. So here's what we're going to do.
Wait, I have a quick question. At
Yeah,
the top
go for
of the
it.
screen, it has a it shows like the Laplace transformation and like the function. Why is the Laplace symbol to the exponentiated to the -1 power on the left?
We'll talk about that later. We'll get there. We'll get there. All right. So here's what I'm going to do. I'm actually going to download this real quick, which I think is silly because I already have it on my computer, but it's going to be faster for me just to download it. And then let me go ahead and open it up because now I can draw on it. And here's what we're going to do. Let's actually get a Laplace transform. And let's find the Laplace transform of, how about we go with e to the minus t cosine of 3t. So we'll use our chart to help us figure that out. So we're going to go down until we see a form that looks like e to the minus t cosine 3t. And we don't have to go very far. In fact, here it is. It's number 20 on our list. E to the at cosine of bt. So we're going to use this one where a is -1 and b is 3. So that's going to give us s plus 1 over s plus 1 squared plus 9. So we can thank whoever it was that already did this for us, that we were able to just plug the numbers straight in to find that the Laplace transform of this thing is s plus 1 over s plus 1 squared plus 9. Ta-da! All right, so how are you feeling about what the Laplace transform is? I mean, be okay with how it's defined? Maybe a little bit apprehensive about what it's going to be like if you actually have to solve one by hand, and that's understandable. But I'm not going to make you do that. Not. I know you guys know how to integrate if you have to. So we're just going to go with the, yep, these are they. So let's use this information to build them.
Would we have access to this table on an exam?
Absolutely. If we were in-person exams, I would print this out and I would hand you this paper. Since you guys are doing your exams at home and it's open note, open book, I'm assuming that you have access to this. Pretty much anything I put on the Canvas shell, I assume you guys are going to be using for exams. And this is the kind of thing that's totally fine to do, by the way, as opposed to, when you put something into Wolfram Alpha or whatever and say, hey, find the Laplace transform of this function, and it just spits it out. That's not appropriate, but using a table like this is totally appropriate. So I guess long story short, yep, you definitely have access to that on exams. And I anticipate that you would, and I expect that you would. I'm not going to want you to have to do anything by hand on an exam. I want you to use it, not build it. All right. So, yay, that's the Laplace transform. Now, let me actually address the -1 business that we got up here, right? As Jacob saw, and he's like, oh, what's the deal with this? Why do we have a -1 thing there? All right, so what does that actually mean? What's a -1 power make you think?
Makes me think inverse.
Okay, good, because it should. And so what this is saying is that there's an inverse Laplace transform. Uh-oh. And I know exactly what all of you just started thinking. Oh shit. Now we're gonna have to do like an inverse thing on this. Well, the inverse Laplace transform, all it does is it goes the other direction. So think about how the Laplace transform brought you from f of t to f of s, big F of s. The inverse Laplace transform takes you from f of s and brings you back to f of t. It turns out that this transformation is invertible. You can go backwards. So when you get a f of s, when you get the result of a Laplace transform, it comes from only one thing. It is 1-to-1. And that's what makes the Laplace transform even better, is that if you are given a function of s, right? If you're given the result of a Laplace transform, you can actually go backwards and find what the original function was. Okay, so basically it's using that table just in reverse. Okay, now to help you see that, I'm going to get my screen really organized here, because I'm actually going to show you my screen. Let me just move some things around here. Because I want the Laplace transform up, but I also want my whiteboard up. So give me 1 second. We're almost at a point where we can pull this off. All right. There it goes. Let's see how this goes. Okay. So let me change my share here. And I'm totally giving you a glimpse of the behind the screens, right? Oh no, hold on. Where'd my whiteboard go? Oh no. Okay, now you guys just see the whiteboard, right?
Yeah.
Dang it. Okay. Hold on. I got this. Let me stop sharing for a second. Pull this up. All right, this will work. He says, very hopefully, but not really. Okay, let's try this again. Screen share, screen share. All right, so do you guys see a paint window and also Laplace transforms on the other side?
Yeah.
Yep, okay, cool. That's what I wanted to see. All right, so here we go. Let's say that we know, yeah, give me a second here. I don't usually work with paint, so let's see. So let's say, oh, son of a, no, that's not what I mean. Let's go here. No, let's go here. Then small. No, not Q1. Let's just go 1. That's what I want. Okay. I'll make this work, guys. Don't worry. No. That one. There we go. Okay. So let's say we've got this, that f of s is equal to 3s over s squared minus s minus 6. I want to know, what does f of t equal? All right, so if we come back and we look over here at the table of Laplace transforms, we want to look and see if we have a form that looks like this. And you'll notice that we don't exactly, right? There are some that have squares on the bottom. Like, look at this guy, it's got a s squared plus a squared, right? Here's one with a difference of squares, but we don't have anything that's just like s squared minus s minus 6. So here's what we're going to do. Let's actually complete the square on the bottom here real fast. If we complete the square on the bottom, remember the process. You got to divide by 2 and then square. Oh, actually, you know what? Let's not complete the square. I lied. Let's factor this thing. It factors to s minus 3 and s plus 2. So that means that we can now do partial fractions. And we can split this thing apart. All right, so for anybody that uses paint, anybody know how to make this go away? Let's make it wider. Okay, so this would be a times s plus 2 plus b times s minus 3, and we need that to equal 3s. So from that, we get a plus b is going to equal 3. You multiply this stuff out in group-like terms. And then we get 2a minus 3b has to equal 0. And with this, we can solve. I believe that you get a equals 5/3 and b equals, oh no, that's not right, 5/9. Erase that. So a equals 5/9. And then that makes b equal, no, that's not right either. 9/5. Gosh darn it. We'll eventually get there. A equals 9/5. That's better. And so then b is equal to 6/5. Okay, so if you solve that, solve this system, you get a equals 9/5 and b equals 6/5. So that means that if we come back here and we rewrite our f of s, that f of s, it equals 9/5 times 1 over s minus 3 plus 6/5 times 1 over s plus 2. So let me erase all this stuff because we don't need it anymore. Now, in this form, it's a little bit easier to spot things that have these Laplace transforms. So the 9/5 and the 6/5, those are scalar multiples, so they're just going to go along for the ride. They don't actually have anything to do with this. So what we really want to concentrate on, what we really want to look at, are these guys. So let's come back over to our Laplace transform table and see which functions actually gave us 1 over s minus 3 and 1 over s plus 2. So if we come back over here and look, sure looks like this is the guy that we want, right? 1 over s minus 3, that's totally 1 over s minus a. 1 over s plus 2, that's the same thing, it's just our a is a negative. All right, so we'll come back over here. And so this tells me that f of t, the function that we started with for our Laplace transform, is going to be 9/5 e to the 3t plus 6/5 e to the minus 2t. And that's why this table is actually really, really big. Because not only does it give you the Laplace transforms, but it also lets you go backwards. Sometimes we have to do algebra, like in this case, we had to do a little bit of algebra to actually get to the form where we could see what the Laplace transforms are, but you can always go backwards. All right, so that's what that little -1 was. It's just an inverse. And so the Laplace transform is invertible. All right, I'm going to come back to my whiteboard because that was a horrible experience right there. Hold on a second. Stop share. Let's try that again. Okay. I'm sorry, I'm all flustered now. Do you guys see my whiteboard?
Yeah.
Yeah, okay. I gotta clean up my screen here, but I can't do what I need to do. In fact, my whiteboard isn't working. I mean, I can draw, but I can't change anything on it. All right, well, we're just gonna go with it. All right. Anyway, so this is the Laplace transform. Cool. Yay. Now we know how to do it. So what? Well, the so what is going to come here. Let's look at the Laplace transform of derivatives and second derivatives and so on and so forth. So let's just see what happens when we do the Laplace transform of, say, f prime of t. All right, so we'll do what we always do. Just start with definition, right? It's 0 to infinity, e to the minus st times f prime of t. Now, this one, we are going to go through using integration by parts. So I don't know if you guys remember integration by parts, but that's the integral of u dv is equal to uv minus the integral of v du. Hopefully that kind of rings a bell. And for this one, we're going to specifically pick u to equal f prime of t. And then dv is going to be e to the minus st. So we need both u and v. Oh, actually, hold on. I lied. I want it to go the other way around. So u is going to equal e to the minus st. So then dv is f prime. Okay, so then du is going to be minus s e to the minus st. And v is going to be f of t, because the integral of the derivative is the function itself. So if we come back over here, then what we're going to get is u times v, so e to the minus st times f of t, still evaluated at 0 and infinity. And then plus the integral of v du, so that's going to be f of t times s e to the minus st. And again, from 0 to infinity. All right, so let's actually look at this guy. If this is to converge, we're going to have e to the minus s times infinity, f times infinity, minus, when I plug in 0, I get f of 0. And then this guy, I'm just going to pull an s out real quick. All right, now, if this converges, which is the only time we care about this, right? When it converges. But if this converges, oh, got control back, yes. All right, if this converges, this is going to have to go to 0. Because otherwise it's going to blow up. So that's going to go to 0. Now, I want you to notice that this bit That's the integral itself. This is just the Laplace transform of f. Right? By definition, this is the Laplace transform of f. All right, so if we kind of put that all together, what we see is the Laplace transform of a derivative. It's equal to s times the Laplace transform of the function itself minus f of 0. Now, that's on that chart. If you go back and you look at that chart, you'll see somewhere down the line near the bottom, there's the Laplace transform of the derivative, and you get this form right here. All right, now you can do this for a second derivative. If you do it for a second derivative, the integral that you get here using parts is going to require another integration by parts. And what ends up happening, I'm just going to call it y double prime, save myself a little bit here. What you're going to end up seeing is s squared times the Laplace transform of y minus s times f of 0 minus f prime of 0. I guess y prime, I should have called those guys y's. Hold on. Now, I can probably talk you through it so you can see why you get this form. Save us from actually going through the whole deal. Because again, think about this guy right here is going to still be there, the minus f of 0. But because we went through this a second time, that's why it's the y prime of 0. Now, this thing, this integral, is going to give us pretty much what we saw before. So that's going to give us an s times the linear transformation minus f, right? So that's why it's an s squared, and it's s times y of 0. Anyway, so that would be your second derivative, but then you can kind of keep following the process, right? Where you go, okay, well, what if we did it one more time? We did a Laplace transform of y triple prime. Well, you'd get all that and then times another s. So we're going to get s cubed times the Laplace transform of y minus s squared times y of 0 minus s times y prime of 0 minus y double prime of 0. And so on down the line. So let me go ahead and jump back to the Laplace transform here. Sheet, that big. If we go down to the bottom, you can see here are those facts. So that was numbers 35, 36, and 37.
Can you apply the Laplace transformation across an entire equation? Like how you can do one thing to both sides? Could you do that Laplace both sides of a differential equation maybe?
Okay, so before I answer that question for you, Jacob, I'm curious, what makes you think you might want to do that?
I'm thinking that it could maybe unlock a different avenue to solve differential equations.
Yeah. And okay, so the answer to your question is yes, you absolutely can, because it's a linear transformation. And you're exactly right. That is what we're going to do, because we can use that to help us solve differential equations. And that's why we do this. Is it's going to turn the differential equation into an algebra problem that we're going to manipulate and then come back and actually get the answers. But Victor, you are about to say something, please.
Yeah, right now, do transformation of derivative, it's like reduction of order, I guess, or something like that.
Yeah, it's actually very similar. In fact, so look at this. If you take the Laplace of a derivative, it turns it back into something about the Laplace of just the original function. Same thing with the second derivative. This big f of s, that's the Laplace of your original function. And so what this is going to do is basically, it is sort of like reduction of order, where it's going to bring us back to just the original function. All right, so let me show you an example. Let's actually do one, and we're going to take a differential equation that we already know how to solve. Okay, so we're going to take one that the solution is already known. We know very well what it does, but it will help you see why this will work. All right, so let's just say we got this one, y prime equals 3y. And we'll even give it an initial condition. Let's say we know that y of 0 equals 4. So I don't mean to put pressure on you, but every one of you should be able to tell me what the answer to this is right now, like without having to do any kind of calculation.
What is he saying?
Y equals 3 divided by 2 times y to the power of 2.
That actually isn't it, Jacob. You're thinking if this was x or t, and you just integrate.
It should be e to the bigger.
Yeah, so this is y prime equals ky. So this is ce to the kt, which in this case is going to be 4e to the 3t.
Well, I guess I flunked that.
Like I said, I didn't mean to put pressure on you. Yeah, you gave me that guy.
Yeah, fuck.
It's all good. It's all good. All right. So we already know what the answer is. We know it's y equals 4e to the 3t. But let me show you how using the Laplace transform. Using a Laplace transform will get us there as well. That was funny. The border on this whiteboard, I can't see the differentiation between the border, and so I actually ran up onto it, and it tried to make me adjust the size of my box. Okay, anyway. All right, so we already know that's the answer. Now, here's how this whole Laplace transform thing is going to help us out. We're going to start with any differential equation. You can do exactly as what Jacob thought, which is, let's just take the Laplace transform of both sides. All right, so the Laplace transform of y prime, so that was the one that I just showed you. That's going to equal s times the Laplace transform of y minus y of 0. All right, so that's the Laplace transform of y prime. And then the Laplace transform of 3y is going to be 3 times the Laplace transform of y. Now, I do know y of 0. We had an initial condition of 4. So this is s times the Laplace transform of y minus 4 equals 3 times the Laplace transform of y. So what I want to do now is I want to solve this for the Laplace transform of y. I want to get L of y equals. So I'm going to move some stuff around. So I have s times the Laplace transform of y minus 3 times the Laplace transform of y equals 4. Now I'm going to factor out my Laplace transform of y. Whoops, not equals yet. So we have that Laplace transform times s minus 3 equals 4. So the Laplace transform of y is going to equal 4 over s minus 3, which is the same as 4 times 1 over s minus 3. All right, so here's the deal. I know what the Laplace transform looks like, but I want to know what the original function is. So let's jump back over to the Laplace table. And remember what we had, it was 4 times 1 over s minus 3. I'll go ahead and write it up here. So we had 4 times 1 over s minus 3. So the 4 is just a constant multiple, so we know that'll stay as a constant multiple. So we need the form 1 over s minus 3. Well, that's that guy again, which suggests e to the 3t. Excuse me. So hop back over here. So this tells me then that y is going to equal 4 times e to the 3t. Ta-da! All right, now I'm not at all suggesting that for this kind of differential equation, you would use Laplace transforms, because I don't recommend that at all. Because this one, we were able to see the answer very quickly. But it illustrates the process. And I want you to notice this. How much calculus did we do here?
Basically
0.
none.
Yeah, not basically, but yeah, 0. Right? We did no calculus at all. And yet we're able to solve a differential equation. And that's really what Laplace transforms are all about. They're taking us from a world of calculus and moving us to a world of algebra. Now, the calculus has already been done, right? There had to be calculus done to get the formulas for the Laplace transforms and therefore the inverse Laplace transforms and blah, 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 right? But once that was done, now it becomes an algebra problem. So that's kind of the whole point of this, is it's going to allow us to find solutions to differential equations without having to do any calculus. Yeah. All right, so let's try this. Let's make it a bit bigger one. Let's go to y double prime plus 4y equals 1. So this one's not quite so trivial. It's not like you can just look at it and tell me the answer. But you can solve this one. This is another one that you can solve. It's linear second order. So that's one where we create the polynomials, find the roots. Depending on the roots, we get our fundamental set. It now equals 1, which then means, well, we got to find a homogeneous solution, and then we got to use the homogeneous solution to find a particular solution, either by, you know, reduction of order, variation of parameters, and determine coefficients, blah, 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 right? Whatever. Well, let me show you how we get the answer using Laplace transforms. So we're going to do the same thing. We're going to take a Laplace transform of both sides. Right, since it's a one-to-one linear transformation, this definitely works. So now we need the Laplace transforms of these different pieces, right? So we're going to have a Laplace transform of y double prime plus 4 Laplace transforms of y. is going to equal the Laplace transform of 1. All right, so Laplace transform of y double prime. Again, we can look at our chart. I kind of talked you through it. It's going to be s squared times the linear transformation of y. Oh, let me give you initial conditions too real quick. Let's say y of 0 equals 0 and y prime of 0 equals 1. So we got some. Anyway, sorry. So we have s squared times the linear transformation of y minus s times y of 0 minus y prime of 0. So these three pieces came from the linear transformation on y double prime, or the Laplace transformation on y double prime. Okay, so then we have plus for Laplace transforms of y. And then on the other side, 1, its Laplace transform was 1 over s. So I'm going to do the exact same thing that I did over here on this first example, which is I'm going to get my Laplace transform of y all by itself so that we can go backwards. So I'm going to get s squared plus 4 times my Laplace transform of y. Right, there was s squared and there are 4 of them there. That's going to equal 1 over s minus s times 0, or sorry, plus s times 0 plus 1. So I'm just putting in my initial conditions in here. So then that tells me the Laplace transform of y is going to equal, if I get a common denominator here, I get 1 plus s over s. So I get 1 plus s over s times s squared plus 4. So basically, I don't know why. I don't know what the solution is, but I do know what its Laplace transform is. That's its Laplace transform, 1 plus s over s times s plus squared plus 4. So let's go find it. Let's break this apart and kind of work our way backwards and see if we can figure out what this function is. So we'll go ahead and use partial fractions again. So we're going to need a over s and then bs plus c over s squared plus 4. That's how we want to break it down. So that gives us a times s squared plus 4 plus s times bs plus c. And that's going to have to equal 1 plus s. All right, so let's group things by like coefficients. Squareds, I'm going to get a plus b times s squared. For s's, I'm going to get c times s. And for constants, I'm going to get 4a. All right, so let's just start putting this together. So that tells us 4a equals 1. C has to equal 1. And a plus b has to equal 0. All right, so we have a equals 1/4, c equals 1, and then b equals minus 1/4. So the partial fractions on this, this gives us 1/4 times 1 over s. And then we're going to get minus 1/4 s over s squared plus 4 plus 1 over s squared plus 4. So I just double checked. It looks like I transferred everything properly, but there's the partial fractions breakdown of this Laplace transform. All right, well now we get to go look at our chart for these forms. Now, the first one, we don't have to go look at the chart because 1 over s, I already know that's the Laplace transform of 1. So I'm going to go and start writing my solution here. So y is going to equal, well, 1/4 times 1 over s is 1/4. The Laplace transform of 1/4 is 1/4 times 1 over s. Now the other ones, let's go find those forms. S over s squared plus 4 and 1 over s squared plus 4. So we'll go ahead and hop back to the Laplace table. So I needed 1 over s squared plus 4. Well, that sure looks a lot like this guy. Where a would be equal to 2. So the form I really need is 2 over s squared plus 4. Well, I can make it look like that without too much trouble. And then remember the other form was s over s squared plus, or s over s squared plus 4. Well, that's exactly this guy. That's exactly cosine, where a is equal to 2. Okay, so let's go back. And let's take care of those. So the second one is going to give us 1/4 cosine of 2t. Right? The s over s squared plus a squared was cosine exactly. And it was cosine of at, so cosine of 2t. Now for this one, this was the one where we actually needed 2 over s squared plus 4. But that's easy enough to do, right? We just multiply top and bottom by 2. So that's actually 1/2 times 2 over s squared plus 4. So when I bring that back to my solution, I'm going to get plus 1/2 sine of 2t. And so there you go, my friends. There is the solution to this initial value problem. And we did an entirety of 0 calculus. And you should be able to confirm that this is what you get. It's not that terrible. Let me just erase this stuff real quick, and we'll kind of walk through this the way that we know how to solve linear second order differential equations. So think about what the process is when we've got y double prime plus 4, y equals 1. So you start polynomial. Okay, so that gives us plus or minus 2i. So that tells us that the homogeneous solution is going to be c1 cosine of 2t plus c2 sine of 2t. We then have to get our particular solution. This one, since it's a constant, I would make a guess, call it a. So y double prime is 0. Plugging that stuff in, I get 0 plus 4a equals 1, or a equals 1/4. So my solution is, my general solution is 1/4 plus c1 cosine of 2t plus c2 sine of 2t. And then we'd have to use our initial conditions, plug those in to find our c1s and c2s. But you can already see, oh yeah, we're definitely getting this form. So take this for what it is. It's an alternative. It's an alternative to finding solutions that don't actually require any calculus. But on the flip side, it does require algebra. And I know for us, not us, but for us, more algebra is not necessarily a good thing. Right? But think about this as a mathematician. When like we're going through this from the very beginning, calculus was still kind of new. We're not terribly good at it. Algebra, we've been doing for hundreds of years. That's our go-to. And always, if mathematicians can if they can drop down a level, they're gonna. If they can go from calculus to algebra, they're gonna do it. If they can go from algebra to arithmetic, they're gonna do it. Because it is easier. I know you don't think that. You hate algebra. You especially hate things like partial fractions and some of the stuff we're going to have to do here, factoring, completing the square, blah, blah, blah. All right. But the reality of it is, yeah, algebra is actually better. And that was the huge thing about Laplace transform. So, Jacob, it sounds like you were about to say something.
Yeah, this only looks like it'd be a useful way to solve a differential equation if we're given the y prime of 0 and the y of 0 values, right? Or
Okay. Yeah, this method works specifically for initial value problems. Or, I mean, you can do it for a generic initial value problem, but you're always going to end up with like the y of 0, the y prime of 0, things like that. So this one, we pretty much reserve Laplace transform process for initial value problems where we do have some initial conditions.
I think it's much faster, especially if we have technology to do it this way. Because the other ways, there's no way to do it faster. Like if you have A and B, you need to find A and B with YP and then do calculus to YP prime and things like that. And
Yeah.
this, no.
No, I agree, Victor. You're right. Like where this really comes in handy is with those initial conditions. Like think about whenever you've had an initial value problem. I know I get this way. I get the general solution and then I go, now I got to figure out the C1 and the C2. And where I really don't like that is with the C2 or from the derivative. Because the original function, okay, fine. I'll plug in my 0 and set it equal to 4 or whatever. Like that's no big deal. But it's that next step, having to find that derivative. Like think about some of the forms that we've seen for our y. Like not even crazy one, but things that we got from just the basic, polynomial stuff. Like you've got a e to the minus 3t times sine of 2t. You're gonna have to differentiate that using product rule, which then also has chain rule. Oh, and then by the way, we have to combine that with another one that's got the cosine on it. And it's just like, then I got to plug everything in and create my system. And so like, to me, that's the worst part of an initial value problem is actually finding the C1 and the C2. I don't mind going through the motions to find the general solution, because that literally is just do the process. It's the other part where I don't like it. Now, with Laplace transforms, we don't even touch that. Those initial conditions, they just get plugged in as numbers. We don't even have to deal with what the derivatives are or anything, So it's one of those things that for the real basic ones, no, you never use Laplace transform. But for the ones that are more complicated, you absolutely do. And as we go further with this, you're really going to see the benefits, especially when we start talking about piecewise defined functions, because we haven't done anything with those, right? But imagine that you've got a forcing function that's piecewise, that changes. Oh man, that's going to change everything when it comes to differential equations. And if we do it the old way, like imagine you've got a forcing function that has like 3 different rules. You're going to have to find 3 different particular solutions for those 3 different cases, which basically turns it into 3 initial value problems. Yeah, they all have the same homogeneous part, so that's not so bad. But trying to find 3 particular solutions to 3 different sets, like you're going to see that Laplace transforms. Yeah, we don't have to worry about that. We're going to be able to figure out what all the different pieces are much faster using Laplace transform. But that's for another day. I think we're going to go ahead and stop here. And we're kind of in the midst of talking about Laplace transforms. I have no idea which section we're technically in. I imagine I'm bouncing around like crazy in terms of the book order, but we're definitely somewhere in that Laplace transforms chapter. As we go, I'll go back and I'll look and I'll kind of address where everything is so you know where to find it. But we're going to continue this on Friday. We're just going to keep looking at differential equations with Laplace transforms and just get some practice under our belt, but just some things to remember. We are definitely going to be doing completing the square. We're definitely going to be doing partial fractions. You might want to go back and practice that just a little bit because it's sort of the key to being able to do Laplace transform. All right, so with that, we shall stop our recording and call